Hello, everyone. We are back and we are continuing our discussion of section 4.3 basis and dimension. Now, the dimension of a subspace, this is our new term, is the number of vectors in any basis for S. Remember, a basis for S is a set of vectors that spans S and is linearly independent. It's the smallest number of vectors you would need to span S. Okay, so let's look at an example. And I've worked this example out for you. Define S to be the span of the vectors v1, v2, and v3. Okay, so the question posed is, what is the dimension of S? Okay, so the dimension of S is either going to be 0, 1, 2, or 3, because you have three vectors that span all of S, but maybe you can span S with fewer than three vectors. Let's say if any of these vectors were related to one another. Okay, so here's what you do. Take these vectors, form a matrix. Okay, let each vector represent a column in our matrix. Row reduce this. Okay, so what you see here is this matrix row reduces to 1, 2, 0, 0, 0, 1, and then zeros thereafter. Okay, you can observe that vector 2, okay, does not have a pivot in it, and therefore is related to vectors 1 and vectors 3, or vector 1 or vector 3, or vector 1 and 3. Okay, so the span of v1, v2, and v3 is nothing more than the span of v1 and the span of v3. Okay, therefore, these two linearly independent vectors spans all of S. Okay, 1, 3, 1, 5, and 2, 5, negative 1, 7 are a linearly independent set. Okay, because we know that because their corresponding columns in the reduced row echelon form have pivots in them. Therefore, they form a basis for S. And since there's only two of them that are needed to form a basis for S, then the dimension of S is 2. But it's not R2. Okay, it's simply a subspace of R4. Okay, so just because the dimension of 2 is the dimension of S is 2 doesn't mean that it's all of R2. It's only representing some subspace of R4. Okay, so moving forward, we're going to touch on some idea that's related. It's column space, and I think it's in a follow-up section, but we can incorporate it into section 4.6. So let's think of this as a combined 4.6 and 4.7 or 4.8. I can't remember which one it is. Okay, we can think of AX, okay, so some matrix times X, as a linear combination of the columns of A. Okay, so let's see our vectors v1, v2, and v3, multiplying it by some vector x with components c1, c2, and c3. What we end up getting is c1, v1 plus c2, v2 plus c3, v3. So that leads us to a really important subspace that's associated with matrix A, and that's called the column space. The column space of A is the span of the columns of A, which is all linear combinations of the columns. Now, let's see if I can put together a picture that kind of encompasses all that we've talked about. Okay, and I'm gonna, in light of the example that we've just done, okay, I'm gonna make a 4 by 3 matrix. Okay, and I'm going to multiply it by x, a 3 by 1 matrix. What am I going to get out? Sorry, a 3 by 1 vector. What am I going to get out? I'm going to get out another vector. Okay, but the dimension of that vector is 4 by 1. Okay, so really what I'm doing, okay, is I'm taking some vector that's in R3. Okay, so we'll call this R3. And under matrix multiplication, I'm multiplying it by some matrix that's a 4 by 3 matrix and outputting some vector that's in R4. Okay, so let's look at representing the matrix A with column 1, column 2, column 3. These are 3 vectors, each with 4 components. Okay, and let's say it can be row reduced into something that looks like, well, let's say there's a pivot here and a pivot here. Okay, so if there's pivots in columns 1 and 3, okay, that's they're 1s. If we're in reduced row echelon form, there's 0s underneath. Okay, there's no pivot here, so that has to be 0. The leading coefficient is 1, so that's 1, and so we have some number right there. Okay, so take this 4 by 3 matrix, row reduce it. Let's say you get something that looks like this. Okay, well, the first thing to point out is this column, column 2. Okay, there's no pivot in column 2. Okay, so if I were to multiply this matrix by the vector x1, x2, x3, and I looked for the appropriate values of x1, x2, x3 that outputted the 0 vector. Okay, in other words, I'm kind of looking for the null space. What would I do? Okay, well, I would say that x2 can be anything it pleases. Okay, here I'm required to say that x3 is equal to 0. Okay, x2 can be anything it pleases. It's in the second column, so it's kind of my free variable. Okay, and that's actually a term that's defined, what a free variable is. Okay, x2 is representing a free variable. x1 is going to be equal to negative whatever that number is times x2. Okay, and we found null spaces of lots of matrices before, so this is not anything that's new to you. So if you look at the generic vector x1, x2, x3, that when multiplied by a outputs the 0 vector, what you're getting is something that looks like minus some number x2, x2, and 0, which is the same as x2 times negative that number, 1, and 0. Okay, so the null space of A is going to be the set of all linear combinations of the vector, well, whatever this is, negative number 1, 0. This forms a basis for the null space of A. Because it's a spanning set, it's the only way that I can multiply the matrix A and get 0. Okay, and it's linearly independent. Okay, any set with only one vector in it is automatically linearly independent. So what that is saying in our picture here is that we can take a piece of R3, okay, and these are the set of all vectors that when multiplied by A output 0. So we'll do that. We'll send A to 0. Okay, Now there's a whole set of vectors in R3 that don't get mapped to 0. And all the vectors that don't get mapped to 0 is called the column space of A. Now, looking back at our matrix again. Oh, and I should say the dimension of the null space of A, okay, is 1, because this vector forms a basis for the null space of A. So how many vectors are in this list? 1. So there you go. Now, this stemmed from, null space, stemmed from the number of free variables. Okay, you could see that in the row-reduced echelon form of this matrix. Vector 2 is some combination of vector 1 and vector 3. So you can say the span of vector 1, vector 2, and vector 3 is equal to the span of vector 1 and vector 2. Okay. Now, the span of vector 1, 2, and 3, by what we've just described here, is called the column space of A. So the column space of A is the span of vectors v1, v2, and v3, which is also the span of vectors v1 and, that looks like a 2. It's supposed to be a 3. So let's make it look like a 3. The column space of A, which is the span, by definition, the span of vectors v1, v2, and v3, is the same as the span of vectors v1 and v3. Okay, so it's spanned by 2 linearly independent vectors, v1 and v3. So what is the dimension of the column space of A? Okay, well, v1 and v3 span the column space. v1 and v3 are linearly independent, so v1 and v3 form a basis for the column space of A. How many vectors are in your basis? There's 2. Okay, so our null space had dimension 1. Our column space of the matrix A had dimension 2. Okay, and really, what does this all revolve around? Okay, it all revolves around the number of columns with pivots versus the number of columns without pivots in the row-reduced echelon form. So I'll put that in a box here. So looking at the number of columns with pivots, there's 2 of them. That's pertaining to the dimension of my column space of A. Versus the number of columns without pivots, there's 1 of them. And that's correlated to, or I can't think of the word right now, but it corresponds to the dimension of the null space of A. There's 1 column without a pivot, there's 1 free variable, the null space of A has dimension 1. There's 2 pivots that correspond to a 2-dimensional column space of A. And what do we notice about the number of the dimension of null A and the dimension of column A? Well, 1 and 2, that is the same as the dimension of R3. Okay, think of it as kind of like the domain. Okay, it's the set of all vectors that are being multiplied by the matrix A. So we actually have an equation that describes this. The dimension of null A plus the dimension of the column space of A is equal to the dimension of this vector right here. So it's Rn, so that's n. And this is called the dimension equation. Now, the book will call the dimension of the column space of A the rank of A. So, dimension of null A plus the rank of A is equal to n. And what is n? It's the dimension of the vectors that are being multiplied by your matrix A. All right, so I'm gonna stop the video right here, and because there's a lot of theory in this, and I want to make sure that I don't add too much into it. And we're going to be doing examples of it in the next video, okay? But this is a very, very important, short, brief, but very dense video that has a lot of terminology and draws a lot of connections with the stuff that we've learned up to this point. Okay, take care.